Hello everyone, my name is Cassi Coleman and I am a computer science major here at UCCS. Welcome to my lecture on statistical analysis using the paired t-test in SPSS. Today I will guide you through what a paired t-test is, when and why we use it, and how to perform it step by step in SPSS. We'll be using a real-world data set to evaluate whether a specific diet program, the Stillman diet, led to significant weight loss among participants. We'll cover everything from loading and exploring the data set to running the paired t-test, interpreting outputs like p-values, effect sizes, and correlations, and wrapping up with a visual summary of the results. My goal is to not just show you how to run the analysis in SPSS, but to help you feel confident interpreting the results and understanding their real-world meaning. So whether you're brand new to SPSS or just looking for a refresher on paired t-tests, I hope you find this lecture helpful. So let's get started. Here's a quick overview of what you can expect in this presentation. We'll start by defining what a t-test is and why it's such a fundamental tool in statistical analysis. Then we'll take a look at the different types of t-tests. There's independent, paired, and one sample, so you can see when each one is appropriate. Our focus will be on the paired t-test, which is used when we're comparing two measurements from the same individuals. I'll explain why this test is useful and when it makes more sense to use it instead of the other types. Next, I'll walk you through a few real-world examples when paired t-tests are commonly applied, like before and after measurements in clinical trials or behavioral studies. From there, I'll introduce you to SPSS, the software we'll be using. I'll show you how it works and then guide you step by step through running a paired t-test using our data set. After we run the test, we'll break down the SPSS output together, including the means, p-values, confidence intervals, effect sizes, and what all of it actually means. And finally, we'll wrap up with a summary and a few key takeaways. So by the end of this video, you'll not only know how to run a paired t-test in SPSS, but also know how to interpret the results and explain what they mean in a real-world context. So what exactly is a t-test? A t-test is a statistical method used to compare the means of two groups and determine if the difference between them is meaningful, or if it might have just happened by chance. For example, let's say you're testing whether a new diet, a training program, or a teaching method had an impact. A t-test allows you to statistically assess whether the observed change is real or just random variation. One of the big reasons we use a t-test is that it works even when we don't know the population standard deviation, which is pretty common in real-world data. Usually we only have access to a sample, not the whole population, and the t-test is specifically designed to handle that. It estimates variability based on the sample itself, making it especially useful for smaller studies or situations with limited data. You'll see t-tests used everywhere in psychology experiments, clinical trials, business reports, and education research. Basically anywhere people are trying to answer the question, did something actually make a difference? In this presentation, we'll focus specifically on the paired version of the t-test, which is ideal when the same group of individuals is measured twice, before and after some kind of intervention or observation. There are three main types of t-tests, and the one you choose depends on the kind of data you're working with, and more importantly, what kind of comparison you're trying to make. First, the one sample t-test. This type is used when you have just one group and you want to compare its mean to a specific known value. For example, let's say the national average exam score for a statistics test is 75%. You want to see if students in your local class scored differently from that benchmark. A one-sample t-test would let you statistically test if the difference between your sample and the national average is meaningful. It's important to remember here that the reference value, like the national average, needs to be known or assumed based on previous data or a certain standard. Without that reference value, you wouldn't be able to use a one-sample t-test properly. Next, the independent samples t-test. This is probably the most common t-test you'll encounter in research studies. An independent samples t-test compares the means of two completely separate groups. Think about a clinical trial where one group receives a medication and the other group gets a placebo. Or a business case where two different marketing strategies are tested on two different customer groups. In these situations, the groups must be independent of each other, meaning the people in Group A aren't connected in any way to the people in Group B. Their outcomes are completely separate. Then we have the paired samples t-test, which is the one we'll focus on today. A paired t-test is used when you're looking at two related measurements from the same individuals or matched units. For example, measuring blood pressure before and after taking a medication, or weighing participants before and after completing a fitness program. These cases, each before and after measurement is linked to the same subject, and that pairing is what makes this version of the t-test different from the independent samples t-test. Another example would be measuring employee satisfaction before and after introducing a new workplace policy. You're not comparing two random groups of people. You're following the same people across 2 points in time. So you can see choosing the right type of t-test depends not only on what you're measuring, but how your data is structured, whether it's one group compared to a standard, two separate groups compared to each other, or two measurements from the same group across time or conditions. At the heart, all three t-tests is the same core question. Are the differences between these means statistically meaningful, or could they simply be explained by random chance? In this analysis, we'll be using a paired t-test. A paired t-test compares two related measurements from the same group of individuals. It's commonly used in before and after studies, like tracking weight before and after following a diet, or measuring blood pressure before and after starting a new medication. One of the biggest strengths of the paired t-test is that it controls for individual variability. Instead of comparing two different people who might differ in dozens of ways we can't easily control for, we compare each person to themselves. This is incredibly powerful because it removes outside noise, things like differences in genetics, lifestyle, or baseline health, that might otherwise confuse the results. By doing that, a paired t-test helps us isolate the true effect of whatever treatment or intervention we're studying. A simple way to think about it is with this apple analogy you see here. We're not comparing a Granny Smith to a Red Delicious. We're looking at the same apple under two different conditions. That's exactly what a paired t-test does. It shows us how something changes by keeping everything else as constant as possible. Paired t-tests are used all the time in real-world settings. In fact, anytime we want to measure change over time within the same group, a paired t-test is often the best tool. In medical research, paired t-tests are commonly used to compare the measurements like blood pressure, cholesterol levels, or even tumor sizes before and after a patient starts a new medication or treatment. Researchers can use this to answer important clinical questions like, did this medication actually lower blood pressure in the patients who took it? In psychology, you might see paired t-tests used to measure levels of stress, anxiety, or depression before and after participating in mindfulness programs, a therapy session, or even a short-term intervention like journaling or breathing exercises. These tests help psychologists determine whether the change they observe is likely due to the intervention or not just random fluctuation. In education, paired t-tests are valuable for assessing academic growth. For instance, you might measure students' math scores before and after receiving extra tutoring. This allows educators to ask, Did the tutoring program actually help improve performance? Or would scores have gone up anyway, just from time and practice? In business settings, companies use paired t-tests to track productivity metrics, sales numbers, or customer satisfaction scores before and after implementing a new workflow system, training program, or a policy change. Business leaders can then make data-driven decisions. Did the new process really make people more efficient? And finally, in fitness and nutrition, paired t-tests are perfect for measuring changes in weight, strength, and endurance, or even body fat percentage before and after a training or nutrition program. For example, you might measure someone's running speed at the start of a 12-week program and again at the end to see if there's a statistically significant improvement. All of these examples show how paired t-tests help us measure meaningful change by focusing on the same individuals under two different conditions and helping us separate real progress from the random noise. To really understand what the paired t-test tells us, it helps to break down key components that go into it. First, we have the mean difference. This is the average amount of change between the two related measurements. For example, if you measured a group's weight before and after following a specific diet plan, the mean difference would tell you, on average, how much weight change across all participants. Positive mean differences could show gains, like increased test scores after tutoring, while negative mean differences might show decreases, like lowered blood pressure after a medication. Then we have the sample size, usually presented by n. This tells us how many paired data points we're working with. In other words, how many subjects had both a before and an after measurement. A larger sample size gives us more statistical power, meaning we're more likely to detect real effects when they exist and less likely to make errors due to random variation. Next, there's the significance level, also known as alpha. We usually set alpha at 0.05, which basically means we're accepting a 5% risk of making a mistake, falsely concluding that a difference exists when it really doesn't. It's kind of like setting our strictness level for how much evidence we need before saying something is statistically significant. Then comes the p-value, which is what we actually calculate during the t-test. The p-value tells us the probability that the results we see, or results even more extreme, could have happened just by random chance. If the p-value is less than our alpha level, usually less than 0.05, we can reject the idea that the change was random and say it's statistically significant. And finally, we come to the hypotheses. The null hypothesis, or H0, assumes that there's no real difference, meaning whatever intervention we applied didn't actually cause any change. The alternative hypothesis, or H1, says there is a real statistically significant difference between the before and after measurements. All of these components, the mean difference, sample size, significance level, p-value, and hypotheses, work together to guide our decision-making process when we look at the SPSS output. There are the key pieces that tell us, did the intervention make a difference or not? For this analysis, I'm using a simplified version of the built-in SPSS dataset called dietstudy.sav. This dataset includes two types of measurements for each participant, weight and triglyceride levels, sometimes referred to as TG levels, taken both before and after participants followed the Stillman diet program. Looking at the table here, you can see that each row represents one participant in the study. The first column lists their subject ID, which simply gives each individual a unique number. Next, we have their gender, labeled as either male or female. Then we have two columns labeled TG1 and TG4. These represent the participants' triglyceride levels. TG1 is their level at the start of the study, and TG4 is their level at the end after completing the diet. Finally, we have weight 1 and weight 4, which show the participants' weight at the beginning and end of the study. Weight 1 is their starting weight, and weight 4 is their weight after following the diet. Because the same individuals are measured at 2 different points in time, both before and after the diet intervention, this dataset is a perfect candidate for a paired t-test. A paired t-test is ideal anytime you have repeated measurements on the same subjects and you want to see if there was a statistically significant change. For our purposes today, we'll be specifically focused on their weight measurements, weight 1 and weight 4, to test whether the Stillman diet led to a significant reduction in weight. In other words, we're asking, did participants lose weight after completing the diet? And is that change meaningful, or could it just have happened by random chance? Before we dive into running the test, let's take a quick moment to go over what SPSS is and why we're using it for this analysis. SPSS stands for Statistical Package for the Social Sciences. It's a software tool designed specifically for conducting a wide range of statistical analyses, and it's especially popular in fields like psychology, health sciences, business, education, and the social sciences. SPSS is widely used in both academic research and industry because of 2 main reasons. First, it's user-friendly. You don't need to know any programming or coding languages. Instead, SPSS uses menus, dialog boxes, and point-and-click commands to guide you through analyses. This makes it much more approachable for beginners, and it allows users to focus more on interpreting the results rather than struggling with technical software syntax. Second, SPSS is also extremely powerful. It can handle everything from basic descriptive statistics like means, medians, and standard deviations to much more advanced techniques like regression analysis, factor analysis, ANOVA tests, and even predictive modeling. Plus, it's great for working with real-world data sets, like the one we're using today, where data isn't always perfectly clean or perfectly structured. In this presentation, we'll be using SPSS to walk through 3 main steps. First, we'll load a real-world dataset into SPSS. Second, we'll run a paired t-test on the weight measurements to see if the Stillman diet made a significant difference. And third, we'll interpret the results looking closely at our outputs like the p-value and mean differences to draw meaningful conclusions. Now that we know what SPSS is and why it's such a powerful tool, let's jump into the hands-on part of the demonstration. Now that we've introduced SPSS and what it can do, let's take a closer look at the research question that will guide our analysis. The main question we're trying to answer is, does the Stillman diet lead to a statistically significant reduction in weight? This research question helps us define the 2 competing ideas we'll test, known as the null hypothesis and the alternative hypothesis. First, the null hypothesis, or H0, states that there is no difference in participant weight before and after the diet. In other words, according to the null hypothesis, any changes we observe in weight would be due to a random variation, not because the diet itself. On the other hand, the alternative hypothesis, or H1, proposes that there is a statistically significant decrease in participant weight after following the Stillman diet. This is the outcome we're hoping to find evidence for, that the diet had a real measurable impact on weight. Now let's quickly identify the key variables in this analysis. Our independent variable is time, specifically comparing measurements taken before the intervention and after the intervention. Our dependent variable is weight, because weight is the outcome we are measuring to see if it changed. So overall, we'll be using SPSS to determine whether our sample provides enough evidence to reject the null hypothesis and support the alternative hypothesis. In short, did the Stillman diet actually lead to significant weight loss or not? Before running any statistical test, It's important to make sure that the assumptions for the test are reasonably met. If the assumptions aren't satisfied, the results of the test could be misleading, so it's worth taking a few moments to check them carefully. Let's walk through the key assumptions for the paired t-test. First, the dependent variable should be continuous. This means it's measured on an interval or ratio scale, where the numbers have consistent meaning and spacing. Examples of continuous variables include things like weight, blood pressure, cholesterol levels, or exam scores. In our case, we're measuring the weight, which easily meets this requirement. Second, the test is designed for paired observations. This means that each subject is measured twice, once before an intervention and once after. In our study, that's exactly what's happening. We're comparing each participant's weight before and after following the Stillman diet. The key here is that the two measurements are linked to the same individual. Third, we need to check for normality of the differences between the paired observations. It's important to note we're not requiring the original weight measurements themselves be normally distributed. Instead, it's the distribution of the differences, meaning the after minus before values, that should be approximately normal. This assumption becomes especially important when working with small sample sizes. With larger sample sizes, the central limit theorem helps out, but with smaller samples, non-normality can impact the accuracy of the results. Fourth, we want to check that there are no significant outliers in the differences. Outliers, or extreme values, can have a big impact on the mean and the p-value, so it's important to identify them ahead of time if possible. A simple blocks plot or a histogram of the differences can help spot potential outliers. And finally, the measurements should be taken on an interval or ratio scale. This means the values not only have meaningful, consistent differences between them, but also a value of 0 actually means the absence of whatever is being measured. For example, for weight, 0 means literally no weight, so it's a valid ratio measurement. If these assumptions are reasonably met, we can move forward with confidence that the results of the paired t-test will be valid, trustworthy, and meaningful for answering our research question. A paired sample t-test in SPSS. First, I'm going to open SPSS, which launches to a blank spreadsheet-style screen that looks a lot like Excel. And to open the dataset, I'm going to go up to the top left corner and click File, and I'm going to go to Open, and I'm going to click Data. And here is a bunch of built-in datasets from SPSS, so I decided to choose one of these, and I chose a dataset that directly uses a paired sample t-test. So that is going to be the dietstudy.sav. So I'm going to click on that and click Open. And once the dataset loads, I can see all of the variables and participants' data laid out in columns ready for analysis. So here we have the patient ID, we have their age, we have their gender, and gender here is numeric, so 0 is male and 1 is female. And then TG0 represents their triglyceride levels before the diet, and then TG4 is 4 weeks after the diet. So triglyceride levels before, triglyceride levels after. And then we also have their weight. So weight 0 is going to represent their weight before the diet, and then weight 4 is going to represent their weight 4 weeks after the diet. So to perform a paired sample t-test on this data set, we're going to go up to the top and click Analyze. And then down here, we're going to go to Compare Means and Proportions, because that's what a paired sample t-test does. It compares means. And then we're going to click on Paired Samples t-test. And from this, we're going to choose two variables for before and after the diet. So here I want to click weight 0 for my before, and then weight 4 is going to be the weight 4 weeks after they do the diet. So I'm going to click that. and that's going to be my variable 2. And then here I want to make sure that estimate effect sizes is checked, and also that the standard deviation of the difference is also checked. These two are going to be very important in determining and interpreting our results of the test. So after we have all of those checked, we're going to click OK. And then this screen pops up, and these are our results. So to start, we have the paired sample statistics table. We'll see that the mean weight before the diet was 198.38 pounds, and then the mean weight after 4 weeks of the diet is 190.31. That's a mean difference of about 8 pounds, which suggests that participants lost weight after following the Stillman diet. And so next, when we go down here, we see the paired samples correlations. This tells us how strongly related the two sets of measurements are, in this case, weight before and after the Stillman diet. The correlation coefficient is 0.996, which is extremely high and it's very close to 1. That means there is a very strong linear relationship between the two sets of weights. And we can see that the p-value is less than 0.001, which means this correlation is statistically significant. This is expected in a paired t-test since we're measuring the same individuals at 2 different times. Now let's move on to the actual t-test results to see if that drop in weight is statistically significant. And we can find that here in this table, the paired samples test. The first row, or I guess column, tells us that the mean difference in weight was 8.06 pounds with a standard deviation of 2.886 and a standard error of about 0.72. Next, the 95% confidence interval ranges from 6.5 to 9.6, meaning we're 95% confident that the true mean weight loss falls within that range. The t-value is 11.175, and the degrees of freedom is 15, since there are 16 participants. 16 minus 1 is the degree of freedom, n minus 1. Most importantly, we see that the p-value is less than 0.001, which is well below our standard threshold of 0.05. That tells us that the result is statistically significant, meaning that the weight loss observed after the diet is unlikely due to chance. So based on this test, we can reject the null hypothesis and conclude that the Stillman diet led to a meaningful reduction in participant weight. And last, we have the effect sizes, which tells us how strong the weight change was after the diet. The first row shows Cohen's d, which is a common way to measure the effect size. In this case, Cohen's d is 2.89, which is considered an extremely large effect. That means the weight loss we observed is not only statistically significant, but also practically meaningful. The 95% confidence interval for this estimate ranges from 1.68 to 3.89, which confirms that the effect is large and consistent across participants. Below that, we see Hedges correlation, which slightly adjusts the estimate to reduce bias, especially in smaller samples like this one. That value is 3.04, still very large with a tight confidence interval of 1.6 to 3.69. So overall, both effect sizes suggest that the Stillman diet led to a strong and meaningful reduction in the participants' weight. So in summary, participants lost an average of 8 pounds after following the Stillman diet, which represents a meaningful change over a relatively short study period. The p-value was less than 0.001, indicating that the result is statistically significant, meaning it's highly unlikely that the observed weight loss occurred by random chance. We also examined the effect size in Cohen's d was 2.89, reflecting a very strong effect. This tells us that the diet didn't just cause a small or subtle change, it had a major impact on participant weight. Additionally, the correlation between pre and post diet measurements was 0.996, which is extremely high. This strong correlation reinforces the paired nature of our data, showing that each participant's weight change was closely tied to their own before and after results. Altogether, these findings suggest that the Stillman diet was effective in producing a statistically significant and meaningful reduction in weight. Based on this evidence, we can confidently reject the null hypothesis and conclude that the diet had a real impact. To wrap up this presentation, we began by exploring what a paired t-test is and when it's appropriate to use, particularly in before and after scenarios where the same individuals are measured twice. Next, we introduced SPSS as a tool for statistical analysis, highlighting how it simplifies data entry, analysis, and our output interpretation through its user-friendly interface. We applied these concepts to a real-world dataset, testing a research question about weight loss after following the Stillman diet. Along the way, we learned how to run a paired t-test in SPSS and how to interpret the key outputs, focusing on mean differences, p-values, correlations, and effect sizes. And finally, we saw how to move beyond just the numbers, learning how to draw clear, meaningful conclusions that are supported by evidence and not just assumptions. Overall, this process demonstrated how statistical analysis, when done carefully, can help us answer important real-world questions and support confident decision-making using data. Thank you so much for following along.